PV equals nRT is an important equation, but if someone asked why PV must equal nRT, it would be impossible to explain or to derive mathematically. The equation is a combination of 3 experimental observations made by Boyle, Charles and Gay-Lussac, and Avogadro. Working independently, Maxwell and Boltzmann tried to describe gases using the basic laws of physics. The starting point was the very good assumption that gas molecules behave as individual particles with huge voids between them and no attractive or repulsive forces between them. The big conceptual jump was made by Boltzmann. He proposed that at a given temperature, all gases possess the same average kinetic energy for its molecules, and that it's equal to kT, where K is Boltzmann's constant. Note that different gases have the same kinetic energy, so heavier gases must necessarily possess a lower average velocity, and lighter gases must necessarily possess a higher average velocity. Though a gas has an average velocity for its molecules, the velocity of each individual molecule will differ. Maxwell described the distribution of velocities displayed within a collection of gas molecules. As the temperature is increased, there will always be slow-moving molecules, but the average will increase, and the chances of finding molecules with very high velocities will increase as well. Using Maxwell's distribution and treating the gas molecules as hard spheres that will exert a pressure when they hit the surface of a container, one can mathematically derive an expression for PV. It is equal to 1/3 of the number of moles times the molecular weight times the mean squared velocity. We also know that to equal nRT. Therefore, 2 can be equated, and we finish with a formula that gives us the square root of the mean squared velocity. Note that this is not exactly the same as the average velocity, but for our purposes, it's good enough. Finally, when using the formula, remember that we must work in SI units if we are to produce a velocity in meters per second. Make sure that R is equal to 8.3145, and make sure that the molar mass is in kilograms per mole. If all is done well, one should find velocities on the order of several hundred meters per second.